So matrices and systems of equations. So we've been given the equations of three planes and there is no unique solution. Okay, and this matrix C is defined as this. Now if you have a look at matrix C, you should be able to see that these values are the same as the coefficients in our system of matrices. So why is determinant of C 0? That's because the matrix must be singular, which means it doesn't have an inverse, as the system of equations has no solution, no unique solution. So if they had a unique solution, you'd be able to solve it by using the inverse of that matrix. And if it has an inverse, then the determinant is not 0. Right, hence or otherwise find the possible values of k. Well, if you ever see this, it means hence is the easier way to do it, usually. So we're going to have to find the determinant of C and use the fact that that's equal to 0. Here's our matrix C. So for a 3 by 3 matrix, to find the determinant, you can use actually any row you like, but most people usually just go with the top row. So I'm going to take the number 1, and you cross out the row and column that 1 is in, and you multiply 1 by the determinant of what is left. Right. Then I go across, and I go across the row to the next element. So the next element is 1. Okay, but we have to remember our pattern here. So the first one would be positive, but the second one is negative, whatever that value is. So subtract 1, cross out the row and column, and do the determinant of whatever's left. Move along. The next one is k, and this is going to be back to plus. Now you would cross out the row and column k's in and do the determinant of whatever's left. And all of that is going to be equal to 0. Okay, so now I go along and work this out. So determinants in the 2 by 2, so that's negative 1 times 0, subtract 14k. Subtract. Right, so that's 3 times 0, subtract 1 times 14. And this is 3 times k, subtract 1 times negative 1. Then we're going to simplify all that. Okay, and then you can just solve that quadratic equation. Okay, so we've got two possibilities. K could be 7 over 3 or k could be 2. Right. Okay, so now we found two values for k, and saying us there's two possible geometric configurations for planes, and we want to identify each and with the value of k. So, part B. We're going to take each value of k in turn. So first one, k is 2. That gives me the system of equations x plus y plus 2z equals negative 2. 3x minus y plus 40. Now, if you have your calculator, you can plug those into your equation solver mode, and you can find out what your solution is going to be before you even start, so you know where you're heading. If you have a class whiz, it will tell you there are infinite solutions. If you have a graphical, it will tell you there are infinite solutions, and it will give you the equation of the sheaf as well. So, what can we do? Well, I've got 3. I can take equation 3 and I can rearrange that to say x is negative 5 take away 2y. I can then substitute 3 into equation 1. So x is now -5 take away 2y. And I can rearrange that equation to get -y plus 2z equals 3. I can then substitute my equation from 3 into equation 2. And if you rearrange that, you should be able to also get that to -y plus 2z equals 3. And so we can see that these equations are consistent, and therefore it forms a sheaf. Then we go with our other value for k. So k is 7/3. Right. If you do the same thing again with your equations, so rearrange 6 to x equals, for example, substitute into 4 and 5, you should find in this case the equations inconsistent. Also, if you look at them, you can see straight away that none of these are parallel. None of the coefficients on the left hand side here are scalar multiples. You haven't got an expression which is a scalar multiple of another one, so they're not parallel. Therefore, they're inconsistent. Your calculator would say no solutions, and they form a prism. And here you'll have the 3 planes meeting at the sheaf. Okay, once we've done that, it says in part D they form a consistent system, so find a solution. So we want to find the equation of that line where they meet. They've said it's consistent, so that means we must be looking at k equals 2, and we're looking at our equations that we found here. I've already done a lot of work for part D. As you can see, it's worth fewer marks than part C. So in part D, I've got 2 equations now that I know are the equations to do with our sheaf. I've got x plus 5y is -5, and I've got -y plus 2z equals 3. To get the equation of that line, I just need to combine these 2 equations. So this one can rearrange. Okay, and then this one I can also rearrange. Okay, and then you can see I've made them both equal to y, so now I can make all these expressions equal to each other. And that will give me the equation of the sheaf, which is therefore a solution. Of course, you'll be careful not to miscopy your answer, which is what I've just done here, because that should be a 2, which makes that a 2, that a 2, and makes that a 2. Your final answer. You can also write this in vector equation form if you like, and if you'd solved your equations differently, you could have x equals or z equals. Your calculator, if you use the graphical, will give you an answer involving z equals.